It's another good day to have you. This is 300 plus academy where all we do is exams tutoring. So, what we have for you today is on the beautiful subject of chemistry. This time around, talking about change of state. I haven't looked at the various states of matter, kinetic theory of matter, and intermolecular forces between particles of materials. Today, what we'll be looking at is detailed explanations of the various change of states. You recall we talked about this in the last lecture, which of course you're going to get the link to the last lecture in the description to these videos. Also, do not forget subscribe to this channel and turn on the notification bell so that at each time that we drop lecture videos, you get notified and you get into the fray of things. Okay, let's move on. Last time out, we talked about various change of state, solid changing to liquid, liquid becoming gases, gas becoming solid, solid becoming gas, and the likes, depending on maybe it has been added or it has been removed. All you need to do to predict that is this material moving from a higher energy state to a lower energy state, or is it moving from a lower energy state to a higher energy state? Of course, the very first one we'll be looking at today is solid moving to liquid, and that is melting. How does melting happen? How does melting occur? This is by addition of heat. When heat is added to solid particles, the particles of solid absorbs the heat energy, making the particles of the solid to acquire more kinetic energy. This is it. We have solid and then we heat. The heat energy is going to where? Is going to the particles of solid. So if the heat energy is going to the particles of solid, it simply means the particles of solid now acquires more kinetic energy. And the result of that is the particles of solid vibrate more vigorously. If they had been vibrating this way before, now that they had acquired more kinetic energy, then they vibrate more. If they've been vibrating this way before, and suddenly you've now added heat and they've absorbed the heat, and what will now happen is that the particles of solid now vibrate more often and more vigorously, and that will make them push neighboring solid particles farther apart. The pushing of those particles farther apart is what will transit the solid, the material from solid to liquid. Look at it like what I wrote on the board. I said the particles vibrate more vigorously, pushing neighboring solid particles farther apart. Recall that for solid particles, they are closed and well knitted together by strong cohesive force. But now that they had acquired more kinetic energy and could vibrate more vigorously, they push neighboring solid particles further apart. Now, the vibrational energy exceeds the binding force, exceeds the cohesive force. And once that happens, the crystalline structure of the solid suddenly collapses. Look at it. When the particles had acquired so much energy and they vibrate with very high kinetic energy, if that vibrational energy exceeds the binding force, of course, you can call that cohesive force or intermolecular force. The crystalline structure of the solid is going to collapse, at which point you say the solid had actually melt. Simply, melting occurs when vibrational energy, as a result of the heat energy, is now greater than the binding force. At that point, a solid is going to melt. Need I say here that impurity lowers melting point of solids, which means that if I have two solid, let this be solid A, ice, no impurity, that is going to melt at 0 degrees Celsius. But let's assume I have impurity in ice B. I could do that if I sprinkle salt on ice B. If I do that, the solid will melt even before getting to 0 degree Celsius, and that tells you that presence of impurity lowers the melting point of solid. We can back this up with a UTME question. Look at, as you can see on your screen, it says UTME 2008 question 2. In countries where the temperature falls below 273 Kelvin, salt is always sprinkled on the icy roads in order to, and you have options there. Why are we sprinkling salt on the icy road? We want, it is simply because we want the ice to melt faster. Why will the ice melt faster? It is simply because presence of impurity lowers melting point. Look at it. Salt is always sprinkled on the ice road in order to lower the melting point of ice, increase the density of ice, make the ice impure, raise the melting point of ice. No, the correct option there is A. Look at another question, UTME question 13, UTME 2013 question 2. The presence of an impurity in a substance will cause the melting point to reduce. It decreases the melting point temperature. So don't forget that. This here is also a UTME question. When does a solid melt? When does the crystalline structure collapse? When vibrational energy or the kinetic energy exceeds the binding force. Also take note that impurity makes ice melt very quickly, even before it attains the melting point temperature. So invariably we say it lowers the melting point. Yes, moving on, I haven't talked about melting. Let's quickly talk about evaporation or vaporization. You see, during melting, the solid had become liquid. The particles more spaced out now as they had acquired more kinetic energy. Now, during evaporation, evaporation happens when a liquid turns into gas at temperatures lower than the boiling point. This is what I'm trying to say. Evaporation happens when a liquid has not yet attained its boiling point. It happens when a liquid turns to gas at the temperatures lower than the boiling point. That is, when liquid changes to gas, when that liquid had not yet reached its boiling point, then we call that process evaporation. And you need to understand that, let's assume we have a liquid here. The moment we begin to heat the liquid, what happens to the liquid is it occurs because some particles have enough energy. As we supply heat energy here, the heat energy is going straight to the liquid particles. So some of those liquid particles are going to acquire, very high kinetic energy, enough for them to break off the surface of the liquid, in which case we now call the process evaporation. I said that it occurs because some particles have enough energy to escape into air from the surface of the liquid. Now, it might interest you to know that there are liquid that even without heating on their own at room temperature, they have the ability to change from liquid to gas. One of such example is petrol and perfumes, you see, and those are volatile liquids. Liquids that evaporate quickly at room temperatures are called volatile liquids. During evaporation, once a liquid is heated, the heat energy we are supplying is going straight to the liquid particles. So in which case we say the particles of the liquid here acquire more kinetic energy. Now, with increased kinetic energy, as the energy of the liquid had increased now, the liquid now has the capacity to break off the surface of the liquid to become gas. That is what evaporation is. If the liquid had not yet attained a boiling point, the process of liquid acquiring so much energy enough for them to break off the surface of the liquid and become gas is called evaporation. Emphasis on when boiling point has not yet been attained. So when the temperature is lower than the boiling point, that is called evaporation. Now, evaporation takes place at all temperatures. You need to know that all that is needed for evaporation is just for the liquid to have acquired enough energy. But you need to know this. Let's say we have water here. the rate of evaporation, let's say at 50 degrees Celsius, cannot be up to the rate of evaporation at about 80 degrees Celsius. Because why? At 80 degrees Celsius, the liquid particles would have acquired even greater kinetic energy than at 50 degrees Celsius. So we say the more the temperature, the more the rate of evaporation. That's why I said evaporation rate increases with increased temperature. Since evaporation, now take note of this point, very important. This explains why evaporation causes cooling. Now, let's assume I have this and I stop applying it. This is what will happen. Those particles of liquid that had acquired enough kinetic energy, they break off the surface of the liquid. That is, the escape of the surface of the liquid, leaving behind those particles that are less energetic. So think about it. If the energetic particles that had absorbed enough heat energy are escaping from the surface of the liquid, leaving behind those that are less energetic, then it means that the temperature is not going to be as high as before. Look at it. Those particles that are escaping here are particles with enough kinetic energy, in other words, with enough heat energy in them. If those particles with heat energy in them had escaped, leaving behind those with minimal heat energy in them, then we can conclude that evaporation causes cooling. And you need to also understand that evaporation always takes place not all over the liquid. No, it takes place or happens at the surface of the liquid, where those liquid particles that are acquired enough kinetic energy can break off the surface of the liquid. So that ends evaporation. Now, looking at that, we've moved from solid to liquid, as melting, from liquid to gas, that's evaporation. Now, let's take the reverse. Let's go back. Okay, let's assume we have a situation where liquid had become vapor, which that is evaporation. Let this be such that this is a closed system. Now, let this be a closed system, a closed vessel, such that we now have a lid, LID, or what you call cover. Let's now have a lid or a cover over the liquid, such that the particles of the gas, the vapor, now they are not able to escape. As soon as they touch on the lid or the cover, which is at a much lower temperature, which is colder, what happens to the escaped particles or the gas or the vapor is that they change back to liquid. Why are they changing back to liquid? Very simple. Simply because they are not able to escape, and then they had touched on, or they had bombarded the cover or lid, which is at a much lower temperature, thereby bringing down the temperature of the vapor, and then they change to gas, a process we call condensation of gas or liquefaction of gas. Look at what I wrote here. I said condensation is the reverse of evaporation. Escape particles bombard the lid or any body which is at a lower temperature. In this case, these are the escape particles. They bombard the lid, which is at a lower temperature. So long as that had happened, then it's going to lead to a decrease in the kinetic energy of the vapor as the vapor loses heat to the lid or the cold body. Look at that again. The escape particles, they are not able to escape. They therefore bombard the lid or the cover, which is at a much lower temperature, thereby bringing down the temperature of the gas or vapor, and as such, they change back to liquid. You see, this leads to a decrease in the kinetic energy of the vapor as the vapor loses heat to the lid or cold body. Temperature of the vapor drops, changing them back to liquid. This is it. Evaporation of liquid is as a result of increase in temperature. But when it comes to condensation, the vapor of condensation of vapor, the temperature drops. The temperature drops. Why? Because the high energy vapor now is losing heat to a much colder body. Also, when talking about gases or vapor, when you compress gases or vapor, they condense or liquefy as well. It doesn't necessarily mean that it has to be when vapor loses heat to a much colder body. When you compress gases, when you compress them into small space, they change to liquid. I think we've done that before. Let this be my gas particles. Let this be my particles of gas. You can see how spaced out. If I compress them into a tiny space like this, if I compress them together, if I compress this together, you see it moves from gas to liquid, and that is what condensation is. Look at what I have in this vessel here with a movable piston. Okay, look at the gas particles. If I push down and I squeeze the particles of gases into the small space, then they suddenly become liquid. Why? Because they had been compressed. And that is why your body spray is able, when you check, it appears as though it's a liquid in its containing vessel. That's because it has been compressed. But the moment you spray and you release it outside, it suddenly turns to a gas again. So what am I trying to say here is that when you talk about gases or vapor, when they are compressed, they condense or liquefy. That's condensation happens or liquefaction happens. So that ends that condensation happens when vapor or gases loses heat to a much colder body, changing them from gas to liquid, or when you compress them. Yes, moving on, you need to also realize that this is chemistry. This is not mathematics like some of us like to view things. No, so you cannot just expect, oh, let's just move straight and get into solving. You have to deal with chemistry the way it should be dealt with. You cannot just know, okay, you cannot just know evaporation without really knowing what it is. You cannot just know melting without really knowing what it entails. You cannot know what boiling is without knowing all of the processes that comes into play. It is chemistry. So what we do is to know, not just to memorize formulas and random stuff. No, we have to understand, we have to know, and that is the more reason why we are looking at detailed explanation into the various change of states and all of the physical processes. Moving on now, we talked about evaporation. Now, let's assume that we have a system like this where this is our liquid here. This is our liquid here. Once it is subjected to heat, of course, once we heat this, what happens is that the particles evaporate. Now, let's assume that as the particles of liquid change to gas, and those particles of gases are not able to escape. What happens is that the particles of gas begins to bombard the walls of the vessel, and they begin to bombard the lid. Okay, let this be my lid or the cover as it is. If the particles of gas are not able to escape, that's if this is happening in a closed system. When you heat, the particles of liquid acquire enough kinetic energy, evaporate, and becomes gases or vapor in the space above the liquid. And what they then do is that they begin to bombard the walls of the vessel. They begin to collide with one another. And as they begin to do that, they constitute what we call vapor pressure. Remember that pressure is force per unit area when something, in this case, particles of gases, that's vapor, bombards or heat on the walls of the vessel and on the lid. So that way they constitute vapor pressure. I said there, as gases escape into the space above the liquid, into the space above liquid, following evaporation, the gases constitute vapor pressure. Why? Because they bombard the walls of the vessels, and as they bombard the walls of the vessels, and as the molecules collide with one another in a closed system. So that what happens there is that when evaporation happens, the particles of gases begins to move randomly, bombarding the walls, constituting or creating what we call vapor pressure. Then you also need to understand that there are those particles that when they hit on the lid, they will change to liquid, they will change to liquid. And there are some of those particles here in the space above the liquid that they are going to touch back on the surface of the liquid, and therefore changing back into liquid and moving into changing back to liquid and moving into the liquid here. In this case, we say they recondenses. So two things are happening here: evaporation, and then secondly condensation. Look at that. It says simultaneously some of the vapor recondenses back into the liquid as they bombard the lid and touch the liquid surface. When the space above the liquid can no longer take more particles from evaporation, what you then have is a situation whereby a number of particles escaping. Imagine that the surface here can take 100 particles of gas, of the vapor. If I continue to eat and let's say like 3 more particles suddenly evaporate, then 3 out of this 100 here must be pushed back into the liquid if 3 had escaped. So what we are basically saying here is that they are in a closed system. There is a tendency of your liquid when we eat to change to gas, and then there is also the tendency of some of those particles of gases above the liquid recondensing back into the liquid. But this is it. If we continue to eat, a point will be reached where number of particles escaping into the space above equals to the number of particles recondensing or condensing back into the liquid. I say again, let's assume that we have that 100 particles can stay up here above the liquid. If we eat, let's assume forcefully we eat now, and about 3 particles evaporate now. If the 3 particles escape into the space, of course the space above is already occupied and cannot take more particles again. If 3 particles should then escape, then 3 particles have to then recondense back into the liquid. The implication of this is that we cannot have more than 100 particles just above the liquid. If that be the case, what that means is that the vapor pressure will remain constant. The vapor pressure will remain constant because at that point, number of particles that will escape into the space above will force the same number of particles to recondense back into the liquid. Number of particles condensing into the liquid. If that be the case, then we have a case on our hand, and that is what we call saturated vapor pressure, which simply means that the vapor pressure cannot rise again because the rate of evaporation now is equal to the rate of condensation. Number of particles leaving or escaping from the liquid equals to the number of particles recondensing or moving back into the liquid, and that is the case of saturated vapor pressure. Also, you need to understand that the air around the atmosphere around us contains air, and therefore we talk about atmospheric pressure. Look at it. So let's say this is a vessel containing a liquid, and when we eat, of course evaporation occurs this way and condensation occurs this way. Recall that we had said that when the rate of evaporation, particles that are escaped here, equals to the rate of condensation as particles that are condensed into the liquid, then the vapor pressure will be constant, a situation we call saturated vapor pressure. But the air around us, the atmosphere around us, you understand, the atmosphere around us contains air. We therefore talk about the air bombarding, therefore talk of the air, of course, bombarding or eating on this vessel. Therefore, we say atmospheric pressure. Air is present, you can see on the board, air is present in the surrounding atmosphere. Air is all around us. Hence, we talk of atmospheric pressure because it means the particles of air will also bombard everything around it. The atmospheric pressure at the level of the sea, at sea level, is 760 millimeter mercury or 76 centimeter mercury, or 76 centimeter mercury, which is what we call 1 atmosphere. So, since atmospheric pressure at sea level is 760 millimeter mercury, or what we call 1 atmosphere, or 76 centimeter mercury, when the saturated vapor pressure on the inside of the liquid, when the saturated vapor pressure on the inside of the liquid equals to the atmospheric pressure that we have as the air bombards on the outside, the liquid boils, and at that point we see bubble all through the liquid. The temperature at which that occurs is what we call the boiling point temperature. Take note of that. When the saturated vapor pressure on the inside of the liquid equals to the atmospheric pressure that we have on the outside, then the liquid boils and we begin to see bubble all over the liquid. Take note, as we move up away from sea level, air pressure decreases, and the reason is very simple. The farther we travel away from sea level, the lesser the amount of air we have in the atmosphere. So when there are less air to bombard, it means as we travel away from sea level, atmospheric pressure reduces. I said there, as we move up away from sea level, air pressure decreases. That is, air pressure decreases with increasing height as we travel upward. For example, at sea level, our atmospheric pressure is 760 millimeter mercury. But imagine we have traveled to about 2,000 meters to the top of a mountain. At that point, the atmospheric pressure may have decreased to about 700 millimeter mercury. So which means the farther up we go, the lesser the atmospheric pressure. And the implication of that is this: it is easier for me to attain a saturated vapor pressure of 700 millimeter mercury, so that boiling takes place very easily, than to attain an atmospheric pressure or saturated vapor pressure of 760. So the implication is that liquid boils with increasing height. Liquid boils at mountain top than at sea level. I said here, the result is that liquid at B will boil first as saturated vapor pressure of 700 millimeter mercury is attained before saturated vapor pressure of 760 millimeter mercury does. Liquid boil easily on top of mountains than at sea level due to decreased atmospheric pressure. It's a very simple thing. The farther up we go, the lesser the amount of air we have around to bombard, to create a atmospheric pressure. So that it means that at sea level we have so much air, it means increased atmospheric pressure. If we travel to mountain top or hills, it means that we have less air to bombard, and that means less atmospheric pressure. Less atmospheric pressure means that it is easier for me to attain that saturated vapor pressure on mountain tops than at sea level does. If I start boiling the same quantity of liquid at the same time, the one on the mountain top is going to boil first. Why? It is very easy for me to attain the decreased atmospheric pressure or saturated vapor pressure up there than at sea level. Lastly, let's not forget that we had said that when the saturated vapor pressure inside the containing vessel equals the atmospheric pressure, liquid boils. Now, the temperature at which a liquid boils is known as the boiling point of that liquid. Now, let's assume that we had attained the boiling point of a liquid, and then having attained the boiling point of that liquid, we have bubbles, we have bubbles all through the liquid, and then suddenly I decide to sprinkle salt into the liquid. What happens? Then it suddenly appears as though there are no bubbles again, as though the boiling point temperature had not yet been attained. Suddenly the bubbles disappears. So what that means is that impurity will now make me have to eat further before I can attain boiling. and therefore we say impurity increases the boiling point temperature. Impurity decreases melting point, but impurity increases the boiling point temperature. Don't forget that, because that it's a JAMB or UTME question. Also, you can as well try out the differences between evaporation, and boiling. Difference between evaporation and boiling. Where evaporation takes place at all temperature, boiling takes place at the boiling point temperature. For evaporation, all that is needed is for the liquid particles here to have acquired enough kinetic energy. But in the case of boiling, it takes place at the boiling point temperature when saturated vapor pressure equals to the atmospheric pressure. Evaporation takes place at the surface of the liquid, whereas boiling takes place all over the liquid. So these are many more the things we need to know. And yes, there are JAM or UTME questions on this, and that is why I keep saying you don't study chemistry as though you're studying mathematics. You have to read to understand. You have to know. That is when you don't have to memorize, and then you can put things in your own words using the right terminologies or terms. With that, we've come to the end of this topic, change of states, a detailed explanation, and looking at things like vapor pressure, saturated vapor pressure, boiling, and the like. Don't forget, subscribe, turn on the notification bell, and share with your peer. From myself and the team, it's bye for now.